wabarakatuh. Hello everyone, my name is Rayya Lintang with student ID 2025-32015 from Information System. In this video, I will explain every single part of my program in detail, a logistic and package delivery simulation built using stack and queue data structure without using any standard template library. The first thing we define is the packet struct. This struct acts like as the blueprint or template for every single package that will exist inside our logistic system. It has three member variables. The first is integer called ID, which serves as a unique identification number of each package. This ID is assigned automatically using a global counter variable called ID counter, which increments by 1 every time a package is created, ensuring that no two packets ever share the same ID. The second variable is a string called nama, which stores the name of type of inside the package. For example, it could be a laptop. The third variable is a string called tujuan, which stores the delivery destination of the package. For example, Jakarta or Surabaya. This simple yet important struct is the foundation of our entire program, because both of the stack and the queue will use this package struct as the data they store and manage throughout the simulation. Next, we define the node stack struct. Since we are not allowed to use STL, we build the stack manually using a linked list. A linked list is made of A linked list is made up of individual nodes, and node stack represent one of single node inside our warehouse stack. Each node stack has two members. The first is packet data, a packet variable called data, which holds the actual package information stored inside this node, the ID, name, and destination. The second is pointer called next, which is a pointer to another node stack. This next pointer is what links one node to the node directly below it in the stack, forming a chain. So when we have multiple packets in warehouse, each node points to the one beneath it, creating the vertical structure of the stack from top to bottom. Now we define the stack struct itself, which represents the warehouse. It has two member variables. The first is node stack pointer called top. This pointer always points to the topmost node in the stack, in other words, the most recently added package. When the warehouse is empty, top is null. The second variable is an integer called size, which keeps the track of how many packets are currently stored in warehouse at any given time. The second structure initializes top as null PTR and size as 0, meaning the warehouse starts completely empty when the program begins. The isEmpty function simply checks whether top is null. If top is null, this means there are no nodes in the stack, so the warehouse is empty and the function returns true. Otherwise, it returns false. The push function is how we add a new package into the warehouse. It takes a package object as its parameter. First, we dynamically allocated a new node stack using the new keyword, creating a fresh node in memory. Then we fill the node data field with the package we received as the parameter. Next, we set this new node's next pointer to the current top. This is a crucial step that links the new node to the existing stack below it. After that, we updated top to the point to this node, making it the new topmost package in the warehouse. Finally, we increment size by 1 and print a confirmation message showing the package detail. This is the default principle in action. The last package push is now sitting on top, and it will be the first one pop up. The pop function remove and return the topmost package from the warehouse. First, we check if the warehouse is empty using isEmpty. If it's empty, we print an error message and return an empty packet to prevent the program from caching. If the warehouse is not empty, we save the current top node into a temporary pointer called temp. Then we extract the packet data from that node into a local packet variable called p. Next, local packet variable called p. Next, we move the top pointer down to the next node. This effectively removes the topmost package from the stack. Then we call the delete. Then we call delete on temp to free the memory that was allocated for that node. Preventing memory leaks, we decrement size by 1 and finally return the packet data. This demonstrates last in, first out. The most recently added packet is always the first one to be retrieved from the warehouse. The enqueue function adds a packet to the back of the delivery queue. We create a new node queue, then dynamically we fill it with the packet data and set its next pointer to null because this new node will place it at the very end of the line with nothing behind it. Then we check if the queue is currently empty. If it's empty, we set both front and rear to the point to this new node because when there is only one packet in the queue, it is the first and the last packets. If the queue already has packets, we attach the new nodes after the current rear by setting rear next pointer to the new node. Then we move rear to point to this new node, making it the new back of the line. Finally, we increment the size and print a confirmation. This is FIFO. Packets always join from the back of the line. The queue function removes and delivers the packets at the front of the queue. We first check if the queue is empty, and if so, print an error and return to empty packet. Otherwise, we save the current front node into a temporary pointer. We extract the packet data from it. Then we move front forward to the next node in line. There is an important edge case here. If after moving front it become null, it means the queue is now completely empty. So we also set rear to null to keep a both pointer consistent. Then we delete the old front node to free memory, decrement size, and return the delivered packets. This is FIFO, the packets that has been waiting for the longest at the front of the line, always the first one to be delivered to the customer. This function is the heart of the entire program. It is where stack and queue are integrated together. First, we first check if the warehouse is empty. If it is, we cannot move any packets, so we return immediately. Otherwise, we ask the user how many packets to move, then inside for a loop. For its iteration, we call gudang pop to take the topmost packets out of the warehouse stack using LIFO and immediately pass the packets into antrian kirim and queue to place it at the back of the delivery queue using FIFO. This single line pop then enqueue is the bridge between the two data structure, transferring packets from warehouse storage into an organized delivery sequence, ready to be sent out to the customer. So that is the complete explanation of every part of the code. To summarize, we built a stack from scratch using a linked list to simulate a warehouse with LIFO behavior, where push adds packets to the top and pop removed from the top. We built a queue from scratch. Using a linked list to simulate delivery line with FIFO behavior, where enqueue adds to the rear and the queue removed from the front. And most importantly, we integrate both structures together. Packets flow from the stack warehouse through the through to the queue delivery line, and finally out to the customer. No STL was used at any point. Thank you very much for watching, and I hope this explanation was clear and easy to follow.